And now we are going to be looking at finding the derivatives of inverse trig functions. So to start out with the idea here, at least, let me first remind everyone about the basic inverse trig functions. So back in trigonometry, as we have learned, there were sine of x. So now for inverse trig function, we have sine inverse of x. So one inverse trig function we can have here is y equals sine inverse of x. Alternative notation for this, I'm more comfortable with writing sine with the superscript -1 for here for my inverse sine function. But many others of textbooks out there also use this symbol, which is quite commonly used out there as well. But arc sine is another way of indicating that we're looking at an inverse sine of x function. And in addition, we have we also have cosine inverse of x. That's another inverse trig function in our entire family of inverse trig functions. And yes, we will be looking at tangent inverse of x, and there will also be cotangent inverse of x. And so there were 6 basic trig functions. So now we're also going to have 6 basic inverse trig functions. And then the last one on my list here to remind for yourself is cosecant inverse of x. And the one I just wrote here is secant inverse of x, like that. Okay, and so now I am going to quickly erase the board, and let's really get to it. And so again, this class here is a calculus class. So forgive me if I cannot go too far back into introducing the details or the reviewing the concept or the understanding of inverse trig function. But here I am going to take the next step here, assuming anyone viewing this video has already had a good solid understanding of what inverse trig functions are doing and how to operate with them, and at least what they are. So let's now get to it. We're going to now take care of the calculus side of inverse trig function. So instead of calling these the example, we are actually going to be doing some actual real deriving work. We're going to find the actual derivative here. So let's say I'm going to be starting out with given, how about our function here being, let's start out with the first one, sine inverse of x. So sine inverse of x here, and we would like to find, our goal here is to find the derivative dy dx. And so up to this point, for anyone studying and been following my video lessons here, then at this point of learning with me, you shouldn't be any surprised about how I use and why I use this symbol for a situation like this. But this is indicating that we're looking for derivative of this function indicated as the y variable, represented by the y variable, and as a function in terms of x. Okay, so here we are finding the derivative of this function, sine inverse of x. So here's the thing. Even though I'm saying that, I said that I'm not going to go too far back into the review, the understanding of your inverse trig function, but there are a couple of things I have to remind everyone. So first of all, if you're saying that y is a variable that equals to the inverse sine of x, then that means it means exactly the same thing as, because that's the way it is. That's the the way that's what it means by being an inverse sine. So if you are letting, so basically here when you take the inverse sine of a value x, and that outputs to be equal a y variable, that means when you take sine, the ordinary sine of y, okay, it will equal to x. Okay, and so let's take a quick pause here and understanding, and again, even though I don't want to go too far back into the algebra of inverse trig function, but at some point we have to remind ourselves a little bit. So in the role of when you are taking your sine inverse function, then the input here must be a value, a real value. But then the output here, that which goes into that y variable, must be a sort of like an angle. So this is angle. So taking an inverse trig function, specifically in this case right here, inverse sine right here, is going to take an input value and give you an output being an angle. And that's now, and so in that way, on the other form that I've just now reminded everyone, then taking the sine of y, so y here is just like that, it's playing in the role of being an angle. So now sine of y is going to be a real value x, and sine of y can be a positive, can be a negative value. Okay, so that's some reminder. And another reminder, but I'm not going to go, and I promise, I'm not going to go to anywhere further than that. But when you take inverse, sine inverse of an x value, then the domain of sine inverse is the input for sine inverse can only be anywhere from -1 to 1. So a brief explanation, that is simply because, see, look at the equivalency between these two equations. So the variable y equals sine inverse of x, if and only if sine value of the y variable to equals x. So that means x being the input of this sine inverse, but now being the output of this sine of y function. And so in that way, see, think about the output value of an ordinary sine function. It has to be anywhere within, anywhere from -1 to 1, isn't it? Okay, and so that's another reminder. So that's the reason why when we're taking x as the input for an inverse trig function, and specifically here I mean the inverse sine function, then it must be the domain for this sine inverse can only be anywhere from -1 to 1. Okay. And then another reminder, but I'm not going to throw in too much explanations. But so the output of this sine inverse here, the range of this sine inverse is internationally agreed to be output anywhere only from -π/2 to positive π/2. Positive π/2. Okay, so this is the range, and that's the domain. So domain is here. This is domain, and this is the range of your function. Okay, and I wrote these two equivalents so that we can start making use of that when we are about to derive our derivative. Okay. So that's all I need to algebraically remind anyone about the properties, the algebraic properties of an inverse sine function. Okay, so now I am going to step over to my other board, and we are really going to find the derivative of the sine inverse. So just as I have pointed out earlier, then so now what I observed and what we knew from what we knew, if y equals sine inverse of x, it leads to another understanding that cosine I mean sine of y must equal x. Okay, and so now I'm not simply just reminding anyone about the algebra of sine inverse and sine, but now I'm really gonna push forward into this idea right here. So what I see here in front of me so far at this particular step, where I have rewritten my beginning equation y equals sine inverse of x into this other form, this equivalence form, sine of y equals x. But my intention now is that I am going to, from this equation here, now we're going to pretend that x and y are two equal row variables. Okay, so y could be a function of x, even though we already knew, but let's pretend that y is some implicit function of x, and at the same time x is also some implicit function of y. So in that way, my plan for the next step is going to use implicit differentiation in this situation we're having. All right, so you feel free to pause the video to recall for yourself how you can operate with implicit differentiation. Okay, and now when you are resuming this video, I'm assuming that you're already fluent with your skill in implicit differentiation. So here we go. I am going to, and recall for yourself one more time that the problem here was asking for finding dy dx, meaning we treat y as a function of x. So back in my lessons earlier about finding implicit differentiation, I always emphasize the meaning of this symbol here. Dy dx means y is a function of x. So y is being regarded as a function, and x is being regarded as the independent variable. So in that way, so now finding dy dx, y is a function of x. So now what I notice, and maybe let me put in an extra step before I'm really doing the work here. But from this equation, I am going to equally take the derivative in terms of x in respect to x on both sides. All right, and so from this point, now back to what I was in the middle of saying earlier. So now what I notice here, y is a function of x, y is a function of x, but pretend that we don't know, pretend that y is only an implicit function of x. And so inside of y there's an entire function of x, and we pretend we don't know, but at least what I see here is that outside of that variable y we have an expression sine of y. So we have an operation, or in other words, we have an outer function here being the sine function. So we have sine, see a little bit of scratch work here. We have sine, and inside of that we have an implicit function y inside of our sine function. Okay, and so now this is what I am going to, after that reminder about the concept of inside and outside. So now on the left hand side, and at this point I'm assuming that anyone viewing my video here has already achieved some majority in how to apply the chain rules and all that. So I'm not gonna remind too much about the chain rule here. I'm gonna get pretty straightforward. But chain rule says we need to find the derivative of the outside. So the outside here, as I have pointed out, it's the sine function. So taking the derivative here of the outside gives me cosine of y. That's the derivative of the outside. But now chain rule says we need to also multiply with the derivative of the inside. And again, recall yourself the idea about taking implicit differentiation. The entire reason that I leave a dy dx here is simply because that is the derivative of the inside function here. The inside function that we're looking at here is unfortunately only one variable that is implicitly defined as a function of x. We pretend that we don't know what that function is, and because we don't, if we stay in that pretending way right here, then if we really don't know that what that function is implicitly defined for y, then we have to leave the derivative of the inside as an implicit derivative. Okay, so that's the reason why, and everything comes out here is right out from the chain rule. And so now from that point right here, at least I know that I'm done with the left hand side. So let's now move on to the right hand side. Again, the symbol means take the derivative in respect to x. Our term on the right hand side is already in terms of x. And so now things is pretty simple here on the right hand side. It's already a function of x, power 1. So now taking the derivative of a power 1 is simply just going to give me 1. Okay, due to the fact that we're multiplying the power 1 to the front, and basically it's 1 times the x to the 0 because we reduced the original power by 1, but x to a 0 to a power 0 is a 1. So altogether my right hand side has become 1. Okay, and at this point anyone viewing this video again have seen the idea here so often enough. But the next step now is to solve for the dy dx here explicitly. So dy dx, and it's all that idea of using implicit differentiation that's being used here. So dy dx equals 1 over cosine of y. Okay, and so at this point, if this problem simply is an implicit differentiation problem, then I would tell my students, we're done here. But here we only use implicit differentiation as a big intermediate step, but ultimately I need to remind anyone following with my video here is that our function in the beginning was a function entirely in terms of x. And so we are not, if our function started out being a function in terms of x, then we shouldn't leave our final derivative here in terms of y like this. Okay, no worries. There's a way to bring the x variable back in this. Okay, so now a little bit of trigonometry here to be brought back to for anyone's understanding. So I'm going to take a quick pause right here. Let me now remind everyone viewing this video. Since we know the famous Pythagorean identity, sine square of y plus cosine square of y must equal 1. Nobody can argue about this. Okay, there has been so many ways how people can prove this identity. I leave that for you on your own freedom to find your own proof for this again, or you can go back to your own the course in trigonometry before our calculus course here to reveal for yourself how your instructor back then had proven this for you. Okay, here we're gonna just use it. There's a whole world of using this identity right here. Okay, so what I notice here is cosine of y can be involved in this identity, and so since sine square of y plus cosine square of y doesn't matter what value of y is, but that's sum of two squares right here must always equals 1. And so in that way, I am going to rearrange my equation. I'm going to subtract sine square from both sides. Okay, so let me make a little red note right here. So I'm subtracting sine squared of y on both sides. Subtract sine square of y on both sides. Okay, so my resulting equation now is going to be cosine square of y is to equal 1 minus sine square of y. Okay, and now we're getting close. We're getting so close. Now recall for yourself. The line is still here on the board. I need to trigger up your attention for here. But what have we defined right here? I mean, from the beginning definition, our variable y is a function of x as a function sine inverse of x. But that was equivalent to say that sine of y equals x. Sine of y equals x. Sine of y equals x. That means sine square here is going to be x squared because we are going to substitute x for sine of y. So that means one further step, this equation can be written as cosine squared of y equal 1 minus x squared. Okay, all right, and the victory is just right around the corner, because ultimately we're looking for how to re-express cosine of y as an expression of x. That's ultimately what we're looking for. And right now we have came to that point where cosine square of y equals an expression of x already. We're so close. So let's get a little further. So the only famous algebra trick here is to take the square root of both sides. But be cautious. Now when you take, or when anyone take the square root of both sides on any equation, then you know this famous understanding. We gotta take the plus and minus square root of the right hand side. There's a whole world of explanations, but here again I'm assuming that anyone arriving at calculus class, or either you are studying it with me or with any instructor, you should be fluent. So I just briefly remind, when you take the square root on both sides, the right hand side must give you the plus and minus square root. Okay, famous enough? But now, so inside of the square root is that 1 minus x squared, as you have already known. Our very last responsibility here is to decide accordingly, is to decide properly whether we're going to choose the positive square root of 1 minus x squared or choosing the negative square root of 1 minus x squared. Okay, and there will be reasons. There will be the good logical reasoning of how we can successfully choose the correct one. Okay, it's not like, hey, if it's not this one, then it's the other one, or hey, if it's not the plus one, then it's the minus one. And another point to emphasize here is that at this point, the reason we have to only choose one, because right now cosine of y is equal to two separate functions of x. Okay, so let's now see how we can choose here. I need to go back to my earlier board, and all the information is still there. So recall for yourself that the domain of sine inverse of x is, the domain for x is anywhere from negative 1 to 1. That's the domain. Okay, and look at the range here that I also put in a rectangular box here. The range for your inverse sine function is anywhere. So inverse sine functions, as an international agreement, as an international convention, it's agreed to come out with outputs being anywhere from minus pi over 2 to pi over 2. So this is the angle. The angle being the output of your sine inverse function is agreed internationally to be output anywhere from negative pi over 2 to pi over 2. I'm going to repeat a few more times. The output angle for sine inverse is negative pi over 2 to pi over 2. What's the impact of that? The output angle of sine inverse is anywhere from negative pi over 2 to pi over 2. Oh my. If this is a trigonometry class, I would tell my students all day to always have the unit circle in their mind. Have the unit circle in their mind. So I would do the same here. Here's the picture of the unit circle in my mind, and hopefully you have the same. There's the unit circle, negative pi over 2, and so the rotation is here around the unit circle. So minus pi over 2 is the bottom terminal point, and positive pi over 2 is this point right here. So in other words, the output of the output angle that came out from your sine inverse function is being anywhere in this unit circle on the right hand side of the unit circle. Okay, what's the good usefulness of that? Being so, as we have already set our outputs to agree, to be only outputting angle at on the right hand side of the unit circle, then that means now when your angle is anywhere on this right hand side, then what's the cosine value? Think about any random cosine value. Cosine value is the x coordinates on the unit circle. So cosine value on anywhere on this half side of the unit circle here must be a positive value. And that's the huge impact that's now going to drive our decision there. So now, I believe everyone and anyone is ready for this. So now we have all our rights to choose the positive square root of 1 minus x squared expression to be our final cosine of y here. Okay, simply because it came straight out of our definition, our output value for y. All right, so now that means cosine of y according to our logical arguments earlier. So now we are going to choose positive square root of 1 minus x squared. Okay, so after all that work and the logical deriving, so now getting back to my almost finished derivative here, then dy dx currently equal 1 over cosine of y. So that means my next step, which is really at the final answer over here, the dy dx that we were looking for is going to equal 1 over the square root of 1 minus x squared. All right. 1 over square root of 1 over x squared. So ladies and gentlemen, you have found it. That is what we have found here is dy dx, given y equals sine inverse of x, then the derivative of this function dy dx equals, so now instead of writing find dy dx, I'm going to be writing out as a final generalization right here. But derivative of any sine inverse of x function is going to be 1 over square root of 1 minus x squared. That is our derivative. And now, once you will be using that often enough, it will become a formula. I don't recommend anyone to remember these formulas or any of the formulas you've learned with me so far. Know how to derive them. That's always the better idea here. That strengthens your understanding and make your understanding more solid. Okay? And so, alternatively, so now we found the derivative of sine inverse. And so recall that I've been introducing that those alternatives notations. That so now starting out with a shorthand, sort of like a shorthand notation here, the derivative for sine inverse of x. This derivative symbol over here. Take the derivative of sine inverse of x in respect to x. That will give us 1 over square root of 1 minus x squared. Okay, and that is going to be, it's just the same formula. I'm just writing that in a different expression right here, a little shorter than writing it out as 2 lines right here. But now even a shorter form of that, sine inverse of x, taking a derivative, and of course here this prime symbol is simply just assuming whichever whatever the main variable of our function is to be the variable of the derivative. So here it has to be in terms of x. That derivative there equals 1 over square root of 1 minus x squared. Another alternative formula for our derivative of sine inverse function. All right, and so now at this point we are ready for, how about cosine inverse of x? Now I am going to be taking some time erasing my board, and we're going to start heading out for cosine inverse. All right, so now let's again put ourselves in a problem where we're given our function to be cosine inverse of x. Okay, and many people out there also write this cosine inverse as arc cosine of x. Okay, in case you haven't been aware of. So now I can just quickly mention that for you. But it's just me. I'm more comfortable with using the cosine inverse. It's a superscript -1 right here. It's not the reciprocal, it's the inverse of our cosine function. Okay, and so, and then we want to find dy dx. Okay, so once again, the very same instruction right here. We want to find the dy dx of our cosine inverse function. Now I am going to take another minute here to erase my board, my other board, so that I can maximize all that space, and we're going to be working together. So as you're waiting for me to erase the board, feel free to start having some ideas in mind. You can carry out that same generality that we have done in the sine inverse function. And I hope you understand what generality I was talking about. All right, and so now before we start another journey here for deriving our own cosine inverse, the derivative of cosine inverse here, then I need to, again, even though I don't want to go too far back into reminding anyone about the algebraic property of cosine inverse or any of these inverse trig function, but at some point we have to. Okay, so first of all, for cosine inverse, just like the sine, the domain here has to be, or can only be, anywhere from -1 to 1. Okay, because again, I have to remind anyone about this algebraic, quite important algebraic property. If the output of cosine inverse of x equals some y variable, that means that equivalently, that's equivalent to saying that taking cosine, the ordinary cosine of y, will be equals x. And that's the reason. That's the reason why x has to be anywhere from -1 to 1. So now if we're looking at x being the input argument of our cosine inverse function, then the inputs, the domain for our x inputs variable, can only be anywhere from -1 to 1. Okay? And then as far as the range for this inverse function, so still, even though I wrote the equivalent form, but everything I'm saying here, including the earlier work for sine inverse, everything I'm writing here is in respect to, relative to our main function here being the inverse trig function. So right now I'm looking at inverse cosine here. So the range, so this is the domain. This is the domain. Okay. The range for cosine inverse of x, that means the output y value can be anywhere from 0 to pi. Okay, and so it can be anywhere from 0 to pi. And it has been agreed for many generations of mathematicians, to the point that in these days we program this output the same with the sine inverse function. We program all of these into any of our calculators, even the very basic one that operates with trig functions and inverse trig functions. Okay, and so the output angle, so again I need to remind anyone briefly, y value here is actually, or as the output of cosine inverse, it's the angle. So we're taking a sort of like the way how I see it, the way how I taught my trig students, that I see this as a linear distance, and then we turn that into an angle value. So this is range, okay, the output of your cosine inverse function. All right, and that is just simply enough algebraic reminder. Let's now move on to the other board, and we are going to really find the derivative of our cosine inverse of x. All right, so really when I was erasing the board and I was advising anyone who was still waiting for me to erase my board to start having some idea in mind. I hope you had that idea, and now my idea hopefully is the same with what you had in mind. Yes, with now y equals cosine inverse of x. Okay, my advice for you earlier when I was still erasing the board was have some idea and use that idea we've had back in when we were deriving the sine inverse function. That same idea comes back here. If we could say y is defined as a cosine inverse of x, then that means equivalently, we can say that we can argue that cosine of y must equals x. And I'm just using the exact equivalent relationship, these two, from this other board right here. Okay, and so in that way, now what's the advantage of doing that? Now if cosine of y equals x, so again now I'm about to use implicit differentiation. I'm treating y as a function of x, but an implicit function of x. Y as a function of x. Y as a function of x. So now from that point, cosine of y is itself already a function of x, but the way I'm seeing it's outside of this variable y, there's another function outside. So cosine is the function outside of my variable y. And then on the other hand, it's x. And so now starting to use the implicit differentiation, this is what I'm doing. I am going to take the derivative in terms of x equally on both sides. Take the derivative in terms of x. Why take the derivative in terms of x? Because our beginning problem asked for that. Okay, the beginning problem asked for the derivative treating y as a function, and in the beginning y was an explicit function. Y was explicitly defined as a function of x, and then we purposely treat that as an equation. So back in our current step right here, we purposely treat x and y as just some two variables. They are related with a cosine relationship, but in the end, y can be a function of x, and x can right now be a function of y. Okay, and so now back to where I was in the middle of, then we were taking the two equal derivatives on both sides, or in other words, we're taking the derivatives equally on both sides of our current equation. All right, so this time I'm going to go back to my usual routine. I'm going to tackle that down immediately on the easier side, the side that's simpler to handle. The right-hand side is already a function of x. It's x to the power 1, x to the power 1. I can maybe put a little note there to remind anyone. So x to the power 1. And the derivative problem is looking for find the derivative in terms of x. And the term itself has already been explicitly written in terms of x. And so the work is just as usual as the way how you have been finding the derivative up to this point. And so that means I'm going to bring the derivative, I'm going to bring the power to the front, 1 times x to the 0. But 1 times x to the 0, the reason I had that 0 was because, we just simply subtract 1 from that original power. Okay, and so, but x to the 0 is just simply 1. So altogether, the right-hand side becomes 1. All right, and maybe for the next problem, I'm not going to be as much detail about that because I believe I have reminded anyone enough about how to find the derivative on simple things like that. Okay, the left-hand side now. So I got to remind anyone again. We got an outside function. That's why I wrote the cosine, but leaving the empty part here inside of that. Okay, so we got cosine of the being the outside, and inside of this cosine we have a variable y. But the variable y itself is a function of x. Y is a function of x. So that means now taking this derivative in terms of x, we have to use the chain rule. So now the chain rule says, taking the derivative of something like this, where there's clearly an inside and an outside, chain rule now says, take the derivative of the outside first. The derivative of the outside, which is in this case a cosine. So derivative of cosine is minus sine of, now we're keeping the inside variable the same. So sine of y is here. And now chain rule says further we need to multiply that outside derivative with the derivative of the inside. The derivative of the inside means the derivative of y. But again, we're pretending that we don't really have to know what y is as an expression of x. We only know y is an implicit function of x. And so that means here, if we only know y being an implicit function of x, then when we take the derivative of y in respect to x, the only thing we can do, take the derivative as an implicit derivative, like that. Okay? Some kind of derivative that we don't really know what it is, but we're leaving it there. It's a dy dx for this variable. So there it is. Now we completed our chain rule. It is here's the derivative of the outside function, and now it's the derivative of the inside function being right here. All right. So now in that way, just like how we did when we were deriving sine inverse derivative, then here I am, just like that. And the same with the idea of using implicit differentiation. I am going to divide both sides by negative sine of y. And so my next step becomes consequently negative 1 over sine of y. Okay. And so again, we started out with our function being expressed explicitly as a function of x. And we were asked to find the derivative of the function y as a function in terms of x. And so it just doesn't look right to end up with our derivative here supposedly in terms of x, but we see no x, only the y variable. So we need to take some steps to bring back the x expression to substitute for this sine of y right here. All right, and so in that way, now again, very similar strategy that we have done, very similar planning we have done earlier. So we know, anyone up to this point taking calculus knows this. Sine square of y plus cosine square of y must equals 1. That famous Pythagorean identity again. So recall again, quickly looking back at this very last step in our work finding the derivative. We already had a sine of y in the denominator, and so that gives me a plan that, hey, I should write from here, from this identity, I am going to subtract the cosine square of y from both sides. And yes, that's what I'm going to be doing. So subtracting cosine square of y from both sides, I'm ending up with sine square of y is to equal 1 minus cosine square of y. Okay, and so sine square of y equals 1 minus cosine square of y. That means in another step, in the next step, we are going to take the square root of both sides. And just like how we did that in the earlier problem, we have to leave plus and minus sign for our right-hand side expression. And our right-hand side expression, I could have also mentioned. Now, cosine of y, and it's still here, cosine of y equals x. Cosine of y equals x. That means right here, instead of writing 1 minus cosine squared of y in this square root, I can just jump directly into writing that as 1 minus x squared to put inside the square root, because cosine squared of y equals x, so cosine squared of y equals x squared. And so that means now inside of the square root, I'm looking at 1 minus x squared. Okay, and so in that way, now again, I have to remind anyone viewing this video, right now we have not really found the expression, the correct expression for the sine of y yet, because right now we got two different expressions. So we have to make a decision to find out which one is the correct one we're gonna have to use. Otherwise, we can't just take this entire thing. Okay, so let me go back to the other board. So cosine of x has input domains of anywhere from -1 to 1. And the output is being anywhere from 0 to pi for the angle. So let's have that picture about the unit circle in our mind again. For the unit circle, if we're looking at the angle outputs being anywhere from 0 to pi, then that means we're at the upper half of the unit circle. 0 is here, pi is here, and the other bottom half is here. Okay, and so think about it. If we're looking at the upper half of this unit circle, then that means, see, pick a point, pick a terminal point. Now sine value is like this. Pick a different terminal point, but at least keep your terminal points in this upper half of the unit circle. Then this point again, finding the sine value, they're all positive sine values when your angle is in the upper half of the unit circle. So that means, what's the conclusion here for us? That means now in this expression, we know that we're going to have to choose the positive expression, the positive square root expression of 1 minus x squared. For the reason being, sine of y must always be positive in this case, because the output, I mean the y value was being given in anywhere from 0 to pi. So in that way, we chose, and we had to choose that way. Sine of y equals positive square root of 1 minus x squared. And so now in that way, I'm very ready to come down to my final answer. So my final dy dx, currently dy dx equals -1 over sine of y. So now for my next step, I'm just simply going to substitute sine of y by this expression square root of 1 minus x squared here. So that means I'm looking at dy dx is will equal -1 over, and it's the square root of 1 minus x squared. Okay, and that's how we have found our derivative of cosine inverse. All right, so I am going to get back to the other board, and let's formulate the idea here. So we started out with our function defined as y equals cosine inverse of x, and what we have done, we have found, and excuse me for another minute of erasing the board here, but so now the formulation we can have here is, with a given function being y equals cosine inverse of x, then our derivative, the derivative for cosine inverse of x has been found to be -1 over square root of 1 minus x squared. We have found it. All right. And again, in the a couple of alternative notations here, but we're looking at our main function, cosine inverse of x, and we would like to differentiate, take the derivative of this function in respect to x. Okay, and so that's an instruction, an indication of finding the derivative of this function. And so that answer there is simply -1 over square root of 1 minus x squared. That's another formula that's quite commonly written in many textbooks out there. Okay, and another shorter form of this, derivative formula. So it's one formula I've been talking about. It's just here, starting at this point, I was showing the couple other alternative notations of how people have been writing the formula for derivative of cosine inverse. And so even a shorter formula here, cosine inverse of x. But now we take the derivative. And yes, this derivative, this prime symbol here, does assume the the variable here is being x, because pretty much x is the only variable in our expression, then it is safe to use that prime symbol. So now the derivative of cosine inverse of x equals -1 over square root of 1 minus x squared. So that is again another derivative formula, another way of writing, another way of to notate our formula for a derivative of cosine inverse of x. All right, so now I am going to take another minute to erase my board, and let's head out to tangent inverse. And again, as I'm taking my time erasing the board, go ahead and start having some ideas in mind, and I highly recommend that you can start, and you have seen that trick, that idea I've used twice in the two previous problems. And so go ahead and use that idea, that generalization about using implicit differentiation. And hopefully you're going to have some good work before I get started into mine right here. All right, so now we are given y equals a tangent inverse of x. Okay, and so tangent inverse of x, then again with this problem we are asked to find dy dx. Okay, and so now I need to remind anyone about a little bit about tangent inverse here. But tangent inverse, yes, if y equals tangent inverse, then the very similar arguments I've been doing with the two functions we have done earlier, the sine inverse and the cosine inverse, then y equals tangent inverse of x also means the same equivalently as taking tangent of y will equal x. Okay, so tangent of y equals x, or the equivalent meanings y equal tangent inverse of x. And I also need to remind again that for tangent inverse, then we are taking the domain. Actually the domain for x here is all real number. Okay, it's really a capital letter R. It's not an IR. Okay, it's just one capital R, but I kind of double weight that straight line right here of the letter R. So it's the letter R, but I double weight that line right there. Okay, it's a special symbol for all real numbers. So the domain for tangent inverse is all the x values in the real numbers. But now the range. So this is the domain for tangent inverse. Okay, but the range is different. The range is actually being quite restricted. So the y value, the angle that comes out, okay, can only be anywhere between, and strictly between, negative pi over 2 and positive pi over 2. Okay, and meet me outside of these lectures, or try to a way to get a hold of me, or you can do your own independent review right there to find out why, you know, the range here for our tangent inverse has to be a strict, the pair of strict inequalities like that, strictly y strictly greater than minus pi over 2 and strictly less than pi over 2. And so now after that brief reminder, so now I'm going to get to the other board again, and we're going to be ready for finding the derivative. So if starting out with y equals tangent inverse of x, okay, then now we have our right to rewrite, okay, that's equation, that relationship y equals tangent of inverse of x is equivalent to tangent of y equals x. and tangent of y equals x. Now that exact same idea of using implicit differentiation comes back here. So I am going to allow me to get straight into it. Now I'm going to take the derivative in terms of x on both sides. So on the right hand side is one single term, x. I'm going to take the derivative in terms of x. Okay, and so, and now again, what I see here, well, the right hand side is quite simple because everything, well, the derivative here is looking for the derivative in terms of x, and our term on the right hand side has already been in terms of x, so it's just going to give me that straight 1. I have explained at least within this video here, I have explained this is the third time, so I don't need to be too detailed about this on this third time here about why we got that 1. But now again on the left hand side, notice for yourself, which is a little bit of scratch work, tangent is being the outside function, and inside of tangent we have some variable y. But y, the variable y is a function of x. Y is a function of x. How did we know that, or how do we know that? It's from right here actually. This notation, recall for yourself again, this notation is indicating that whichever our current equation is, but we want to purposely treat y as a function and x is being the variable. So in that way, now in this equation that we came to, then we are treating y as an implicit function of x. Okay, and so implicit again just means it is some function, but we just don't have to know. It's kind of hidden. Okay, but so now in that idea right there, along with that idea, then we're looking at an outside function being tangent, and inside of tangent it's a y, but y is some implicit function of x. So in that way, now I keep using the term inside and outside because the chain rule is kicking in again, is going to be applied here. Okay, so the chain rule says take the derivative of the outside. The derivative of the outside. The outside function is tangent. So recall for yourself, it was some lecture before this lecture here that we've looked at how to find the derivative of tangent. So the derivative of tangent here, the outside function, is going to be secant square. Okay, that's the derivative for tangent. Okay, so secant square, and then chain rule says we keep the exact same variable inside the derivative of the outside, and then the chain rule says we must multiply with the derivative of the inside. Okay, so but the inside is just a function that we only know it's implicitly defined, but we don't know exactly what that is. So in that case, the derivative, we have no choice other than writing that derivative as the implicit derivative dy dx. So that it is secant square is the derivative of the outside, and we keep the variable inside exactly the same way it is. Okay, and then we multiply according to the chain rule. Multiply with the derivative of the inside. That's how we ended up with that dy dx. And so now, and of course, equals 1 on the other side. Okay. All right, and so now at that point, now we can go ahead and again divide both sides by secant squared of y. My equation consequently becomes dy dx equals 1 over secant square of y. All right, so dy dx equal 1 over secant square of y. Let's do because I need to remind anyone again, we have just now arrived at a derivative, a final derivative, quite final, but in terms of y. That's not quite what we're looking for, because our function, recall for yourself, our function in the beginning was a function explicitly in terms of x. And we want, so in that way, even if we went with implicit differentiation, but we definitely want to find our way to express our final derivative in terms of x. That will look better, much better. And so in that way, well, let's have some work around right here. All right, so here's the workaround. So this time I'm going to use a different, it's still among that family of Pythagorean identities, but here we're looking at tangent square of any variable, tangent square of y plus 1 is going to equal secant square of y. Okay, it is actually, at least when I teach my, or anytime I teach my calculus students, I would refer to this identity here as a member in the Pythagorean identities. Okay, and other professors might use a different name right here, but I see this as being the same as the Pythagorean identity. Not as famous as the other one though. But anyway, so tangent square of y plus 1 equals secant square of y. That famous, quite famous identity right there. So what's useful about this? Secant square of y can now be re-expressed as tangent square of y plus 1. But not quite too useful yet, because we're still stuck with the with the y variable. But here, didn't we agree that tangent of y equals x? Right at this point right here is perfect for our substitution. We can now substitute x for tangent in our equation here, and then so tangent square means x squared plus 1 has to equal secant square of y. So now if we found a good solution for this, because what it is there now, or maybe I can just write it here in this little space that remains, dy dx that we have come up earlier, now eventually becomes in the next step. In the next step, it's simply just 1 over 1 plus x squared. All right, and that is simply how we found the derivative of tangent inverse. And so let's again formulate a generality here. Our function from in the beginning was the tangent inverse of x, and we were asked to find the dy dx. So now we have found the answer. The answer is simply as a formula now. 1 over 1 plus x squared. That is our derivative of tangent inverse. And so in that way, again, the shorter notations of this formula, when we have tangent inverse of x and take that derivative in terms of x, then we are looking at the derivative here as being simply 1 over 1 plus x squared. That's a different way of writing our derivative of tangent inverse of x. Or we also can use the even shorter form of this formula here, tangent inverse of x. Okay, take the prime. And so again, the prime symbol here in this case assumes the x variable here is to be the main variable. And that equals 1 over 1 plus x squared. And that's another form of writing our formula. One same formula, just different way of how we're writing it. And this one here is the shortest one. And these two forms are quite common among the many textbooks out there on the market. Okay. All right, and I am going to again take a couple minutes to erase my board and be ready. This time I am going to have viewers of mine or even students who study with me here to derive your own derivative, because you've had enough experience at this point right here. I want you to independently derive your own derivative for the next function. All right, so be ready. Meaning I am not going to step in and showing the steps anymore. You are going to derive it on your own, and I'm only gonna say the final answer. Okay, so what about now you have done I have walked you through the step-by-step deriving work for finding the derivative of tangent inverse. So what about you are given cotangent inverse of x? Okay, cotangent inverse of x, and I want you to find, and when I say you, I mean anyone viewing this video. It could be any public viewer or my students who study with me, but I want you to find for me the derivative dy dx here. Okay, so go ahead and grab a piece of paper and a pencil, right? And pause the video and take as much time as you want. Find the derivative here. All right, so I hope you're back with your own answer. So here it is, and as I already said, I am not going to show the steps here anymore. I want you to be able to pull out those steps and do a little research on your own. That's the quality of anyone who is working their way to be a mathematician. Doesn't have to be a formal one. As long as you're doing math with a paper and a pencil, you are in a family of mathematicians. So this is what we're doing. The final answer for this dy dx is going to be dy dx equals minus 1 over 1 plus x squared. Okay, so just as I said, I am going to give just the final answer, and I expect you to have your own. I want you to have your own work for this, your own steps to derive for this derivative. Okay, so that is the derivative of cotangent inverse. Now, sadly, secant inverse and cosecant inverse are quite complicated to find derivative, to have a clear, solid derivative. So I will come back to those at a time later in some other later video lectures, but allow me to end our work here. So after this derivative of cotangent inverse that you actually have found independently on your own, hopefully, then we're gonna start heading out for doing some actual examples right here. But I'm not going to go any further into the secant inverse or the cosecant inverse.